Welcome back to ECE 501B. Homework number 8 is due on Monday, and we have one more week of class. And next week will be our last day of class, and our final exam is a couple of weeks from yesterday, if that sounds right. It's on a Tuesday, it's not on a Monday or a Wednesday, and it will be later in the evening, but it will be scheduled here. And the other thing that we need to worry about is your project, and that's due on the 9th of December. And if you would, I would really appreciate you completing the teacher course evaluations. I assume that you've been getting emails. Those stop, I think, once you complete the TCE, I assume. And those are anonymous, and I use those to help correct or change or modify the course for the next time. And not only are they anonymous, but I don't see those until after your grades have been awarded. So it's not going to impact your grade in any way. It will impact my grade, but I want to get your input on that, and the more I get, the better that overall picture is. If I only get one or two, that's not very good. If I get the whole class, that's much better in terms of participation. Today what I want to do is finish Chapter 10. And with respect to Chapter 10, now because of the way this book is titled, Linear Algebra Done Right, we don't talk about a determinant until the last chapter. So that's where this is coming in, and we'll talk about the trace and determinant. We will then finally answer or get to the material that an earlier question this semester raised, and that was, what is a pseudo-inverse? We will talk about that, where it comes from in terms of underdetermined or overdetermined or indeterminate equations, and how does that arise, what is a formula, and we will relate that also in terms of numerically computing that to a singular value decomposition, and how you can use the SVD to find the Moore-Penrose pseudo-inverse. Then we will talk about principal component analysis, which is one application of what we've been doing recently in terms of creating matrices and finding their principal directions or eigenvectors, and that's related to this principal component analysis. Did anyone in class select that as a topic for your project? Some of you maybe did. So we'll cover a little bit of that. Depending on how much we get to today, I may post a presentation on the PCA in addition to a normal lecture, and that will be in the appropriate location on the D2L website. Then we will get into the second half of the course, the second textbook. We've left a week to cover that, so now we cover 15 weeks of material in a week. That's what you call accelerated learning. But that's the Frank's textbook, and that should be on the resources or under the course resources unit on the content page, and that's now connecting these concepts that we've talked about so far in finite dimensions with infinite dimensions. And instead of vector spaces, now we could think of not vectors but signals or functions, and so it might be called signal space or function space, and that's this infinite dimensional vector space concept. And we might use Fourier analysis to motivate that. That's really what we're doing. We are having orthogonal basis, orthonormal basis in Fourier series or in a Fourier analysis, and we're just adding and adding and adding, and we're always able to add additional or unique information with each eigenfunction that we add in, which is, let's say, this collection of sines and cosines at a given frequency. So we'll talk or try to relate that to what we've done in the past.
Did we complete chapter 9?
So did we complete chapter 9? The question is, that's the question. The answer is yes, but we did it in the form of completing Chapter 8. And so I left it up to you to complete Chapter 9. This is the way that we completed it was at the end of last lecture, I said that. I said Chapter 9 extends these results to real vector spaces, and I may have put that sentence in after you left on Monday. But that's now our coverage of Chapter 9. Pardon? No, somebody just made a comment. So let's now get into Chapter 10. The material in Chapter 9 is consistent with what we talked about in Chapter 8. It's just now focused on this real version of what we talked about with the complex fields, or over the complex fields. Let's now talk about trace and determinant, and these are defined for an operator, or a linear map that maps from one vector space back into itself. So this is now trace and determinant. Of an operator. Suppose we start with a vector space, and let's just specialize that to be a complex vector space. If V is a complex vector space and T is an linear operator on that vector space, then the characteristic polynomial of that operator T is given by Q of Z equaling, do you remember what that was from last time? It was a product of factors that are associated with each of the eigenvalues, and those factors are of multiplicity, or of an appropriate multiplicity, which we were calling d sub 1. This is then z minus, or d sub I, z minus lambda 1 raised to the appropriate multiplicity. If it's repeated, or if it's not repeated, d sub 1 is 1. Z minus lambda sub 2 raised to the d sub 2, etc. And then z minus, let's say that we have m distinct eigenvalues, z minus lambda sub m raised to its multiplicity d sub m. That's the characteristic polynomial from before, and this leads to the following. Q of t, and now this is a matrix expression, t to the n minus lambda sub 1 plus lambda sub 2 plus plus, let's say, lambda sub n, and now I'm including multiplicities in that lambda sub n. So if lambda sub 1 was repeated 3 times, three of those lambdas would be lambda sub 1, is what I'm meaning by that. That's why it's now lambda sub 1 summed up through lambda sub n. T to the n minus 1 plus all the way down to minus 1 to the n times the product, including multiplicities, of these eigenvalues. And in fact, these parenthetical scalars made up of combination of eigenvalues are given or correspond to the particular terms that we said we were talking about in Chapter 10. This sum of eigenvalues is actually the trace of T, and this product of eigenvalues is the determinant. As an example, you can see those two factors fall immediately out if we look at the second order case. Let's say that we have Q of Z. We can do this rather easily with paper and pencil. If we look at Z minus lambda 1 times Z minus lambda 2, this is then Z squared, its second order, which we would expect, minus lambda 1 plus lambda sub 2 times Z plus lambda sub 1 times lambda sub 2. And you can see that that last piece is minus 1 squared, the coefficient on the product of lambda 1, lambda 2, and we have our minus lambda sub 1 minus lambda sub 2. From the characteristic polynomial and plugging that into or applying that to our operator, now allows us to say that the trace of t is this sum from I equal 1 to n of lambda sub I, where this sum of eigenvalues includes the multiplicities of those eigenvalues. But now you might be asking, but how are we going to find that trace? You could find the eigenvalues of that operator and sum them up, but that's a little tedious. There's actually a quicker way. Yes, so you could find the characteristic polynomial and then pull off that n minus 1 power of the z, and that coefficient would be the trace of t with the negative sign factored out. But that's a little tedious also. There's actually a quicker way to compute the trace, and if you've had a linear algebra class, you know what that is. But how to compute the trace of t. If we were looking at the matrix representation of that linear operator, then the trace of that linear operator t is actually just the sum from 1 to n of the diagonal terms in that matrix representation. Meaning if you can now take the linear operator, find the matrix representation of that, now all you have to do is add the diagonal entries in that matrix, and that gives you the trace. And this carries over if we're not explicitly identifying a linear operator and just dealing with matrices. We have the following matrix facts. If we wanted the trace, then the trace of a matrix A is equal to the sum of the diagonal elements in that matrix. That's why the subscripts are the same, A sub I, and that's also equal to the sum of the eigenvalues, where lambda sub L from 1 to n on L are the eigenvalues of the matrix A. We can also talk about or find a relationship on the determinant with our matrix, and a lot of times we just label that or indicate that symbolically as these vertical lines surrounding A, not two vertical lines, but one on either side of the matrix. That's typically used for the determinant of A, and this is now equal to the product, again including multiplicities of those eigenvalues. And you might remember in that earlier first statement that we talked about in class, if we now have this linear operator t, the determinant of t, which we will say is determinant of t, is in fact the constant term in the characteristic polynomial scaled or multiplied by minus 1 raised to little n, where little n is actually the dimension of the vector space V. Suppose we now are dealing with our complex field, and we wanted the determinant of t, and that's this product of I equal 1 to n of lambda sub I, and that includes multiplicities. Now we can talk about the next proposition. Or the next proposition will be, let's say, immediately clear. Question? So this particular expression, the question was, do you have to have your your operator in any form, in any special form, upper triangular form, for this to work? No, you don't. It's clear, it's obvious that the determinant is the product of the diagonal, but if you know the eigenvalues, they haven't changed whether your operator is in an upper triangular form or in any generic form, as long as it's the same linear operator. So as long this formula is true for a given operator, you just have to know the eigenvalues. If you transform it so that it is upper triangular, then it's clean or clear that, oh, my eigenvalues are right on the diagonal. So you could explicitly identify those eigenvalues, but you wouldn't have to if you could find those some other way, and we'll talk about that in just a minute, how we could find those from a linear operator without worrying about, yeah, let me just leave it at that. We'll find those in a minute, but this doesn't depend on the linear operator being in any particular representation. It's just that it's very obvious that that's true when it's in upper triangular form, because the eigenvalues are on the diagonal. But now this proposition says an operator is invertible if and only if the determinant of t is not equal to 0. So now if we know the eigenvalues, or if we know something about the determinant and somebody says, is this linear map or linear operator invertible, if you can see that the determinant is not equal to 0, then you know it is invertible. If it is equal to 0, then you're not going to be able to find an inverse of that operator. And the proof just relies on us remembering a relationship or a fact from earlier in the class. Remember, an operator does not have an inverse, or I will say is non-invertible, if and only if it has at least one zero eigenvalue. a 0 for an eigenvalue. And in both complex and real cases, the determinant of t can be determined by forming a product of the eigenvalues. The determinant of t involves a product of eigenvalues. Thus, if we find that the determinant of t is equal to 0, then we know that at least one of those eigenvalues had to be 0, and if we have a 0 eigenvalue, then our linear operator does not have an inverse. Thus, the determinant of t equaling 0 happens if and only if there exists a lambda equal to 0. Which says that if you were trying to determine, do I have an inverse for this linear operator or for a matrix, if somebody knows the eigenvalues or if they give you the determinant information, you can immediately make that call yes or no. You don't know the inverse necessarily, but you know one exists. Now let me state or make an observation or state a fact. Now that we are talking about determinants and how we can maybe find those, suppose we now have this linear operator t on a vector space V, and let's say lambda and z are over the field of F, so they could be real or complex. Then what we want to say in this fact is, if I know that lambda is an eigenvalue of t, then that's equivalent to saying that z minus lambda, that scalar, is an eigenvalue of zi minus capital T. So if lambda is an eigenvalue of t, then we can also say that z minus lambda is an eigenvalue of zi minus t. That's the fact. And we simply have to do just a little algebra to show that that fact is true. Suppose that I start with zv minus tv, and I'm going to assume v is an eigenvector associated with the eigenvalue lambda. But now I can say that that's z times iv. I can put that identity map in between the scalar z and the vector v minus tv. But if I now say that v is an eigenvector of t with eigenvalue lambda, then I can say that tv can be replaced with lambda v. Here I'm saying v is an eigenvector of t. And on the right-hand side, I can now just collapse or no longer keep that identity map in between the scalar v and the vector v. And now I can Now I have two scalars, z and lambda, that I can factor out of the vector v. I can now say this is z minus lambda times v. But what does this give me? If I factor the v out of the right-hand side of that, I now have this matrix zi minus t times v. And I hope that this structure looks familiar. This is now some operator times a vector equaling a scalar times that same vector. So we're just moving in the direction of this vector by an amount given by that scalar if this is the operator applied to that vector, and this is then just our eigenvalue eigenvector equation. And that's true as long as this vector v is an eigenvector of t. So that now we've basically demonstrated that if lambda is an eigenvalue of the operator t, then z minus lambda is an eigenvalue of zi minus t. And what can we now say? Now we can use this fact to give us a strategy for computing this characteristic polynomial. The above fact lets us compute the characteristic polynomial of our linear operator t via the following theorem. Where the theorem says if we're given a linear operator t on this vector space V, the characteristic polynomial of that linear operator t equals the determinant of zi minus t. So now if you can compute the determinant of a matrix, now you put in this variable z scaling the identity matrix and you compute the determinant of zi minus t, which involves this variable z, and that will now give you the characteristic polynomial of the linear operator t. That's what this theorem is stating. And now we can basically prove that using the fact that we just examined or justified in the previous screen. Remembering what the determinant of t is, that's just the product of eigenvalues of t, and that includes multiplicities. Then we can use the following. We can say, since we know that zi minus t has what as eigenvalues? That map from our fact, we now know that eigenvalues of zi minus t are z minus lambda, or z minus lambda sub I. And from this blue line, we can just generalize that to this expression zi minus t and say, oh, that's the product from I equal 1 to n of z minus lambda sub I, well, that's just z minus lambda 1, z minus lambda sub 2, z minus lambda sub n, and that's actually what we had used or written down as our characteristic polynomial. So this is determinant of zi minus t will give us the characteristic polynomial. And that is because we derived that fact or wrote down that fact a little bit earlier, that if lambda sub I is an eigenvalue of t, then z minus lambda sub I is an eigenvalue of zi minus t. And we know the relationship between the determinant of a matrix and the product of its eigenvalues. That's now what we will say concerning trace and determinant. Let's now look at the Moore-Penrose pseudo-inverse. And this is the same Penrose that is the author of the first 4 chapters of that book, basically a complete guide to everything, or whatever, that I can't quite remember the title, but in the resources to the course, one of those resources was concerning some early chapters in that book by Penrose. And he's a fairly prolific author of more than just sort of math. He blends math and physics. But he now has his name attached to this pseudo-inverse. In this case, let's just start talking in general about a linear map. Suppose you have a map and this map could be a measurement system. Meaning you might know that you have a map between some input vector and an output vector, where the input vector is coming from a vector space U, and the output vector is coming from an output vector space capital V. Meaning now maybe we have M equaling the output of T that's mapping W through it, where W is coming from a finite dimensional vector space, let's say of dimension capital N, and the measurement or the output M is an element in our output vector space capital V, and let's just assume that that one is of dimension M. So we can make capital N and capital M different if we want. And the idea here is maybe we can measure M, but we would like to figure out what W is by measuring M. Maybe we're not measuring W directly. Maybe all we can do is measure what's coming out of M. And we want to, from the measurements M, figure out what W is. That's our idea. So we wish to use the output vector little m to infer something about the input vector W. Or we're really looking for answers to the following question. What is the best linear method for estimating W from M? So we're measuring M. We don't know what W is, but we want to try to find the best linear method or the best representation of W from the measurements M. And to establish some notation, let's just assume that this estimate we'll call W hat. The real W is W. Its estimate is W hat. I'm going to then say let's define W hat to be the estimate of the true vector W. So now let's look at some potential answers to this question. We have this relationship between M and W. We want to now try to estimate W when we can't measure or we don't know W explicitly. Let's say answer 1. Suppose that our input space and our output space are the same. What's that imply about the linear map T? It's an operator now, so we can now say T is this linear operator on U. And if that linear operator is full rank, do we remember, did we say rank at all before in this class? Have we used that term or expression? We haven't. Full rank means that this linear operator has linearly independent columns or rows, or it has a non-zero determinant. All of the rows and columns associated with this, let's say the matrix representation of T, would all be linearly independent. So we have a full rank T. The matrix representation of T is square, and now we're saying that all of the rows in that matrix or all of the columns in that matrix are linearly independent. Then the best or in terms of a linear operator, T is injective, T is surjective, or T has an inverse if it's full rank. Then the best estimate is in fact exact, where W hat is now T inverse times M. So if somebody gives us M and we know T, and we know T is full rank, we've maybe calculated the determinant of T and we found that the determinant is non-zero, then we can get the inverse. But M, based on the relationship that we said it had with W, M is just TW, and T inverse T is the identity, so now we can conclude that the best estimate of W, if T is full rank, will just be the actual true W itself. So now we're using this relationship between M and W to show that, in fact, the best estimate is indeed the actual vector. And we can do that because now the inverse of t exists. Suppose that the inverse doesn't exist, but maybe we still are dealing with a linear operator. Suppose that u is equal to v, so this is answer 2, but t being this linear operator is not full rank. Now I can start using my cloud pictures again. What does this mean by for t? We're now assuming that u and v are the same, so just remember that those are the same, so I'm really mapping back into itself, but now I might have, for example, all of these vectors might actually map to the same point. I may have a non-trivial null space. And that may be true for multiple vectors in the vector space U. So in this case, this is my linear map T, but T is, let's say, many to 1. Or another way of saying that is it has a non-trivial null space, or it's non-injective. If that's the case, we have no inverse. And we also know that T is not going to be covering, or we can't get to every vector in U or V from T, because it's non-surjective. In this case, many vectors map to same vector, and that's what we're meaning by non-injective. So this is what we're trying to obtain for answer 2. So now we're saying, what about the case where we do have a linear operator, T, but it's no longer full rank? We can't just compute the inverse of that linear operator. Then that introduces another question. Let's call it question prime, because now we might end up with many different W hats. We want to know what's the best W hat. We might have many W hats that solve or that give us a result. Which of many possible best estimates W hat should we select or pick? And our answer to question prime, let's say, is now our answer prime. We want to pick the best W, or the best estimate, pick the W hat with the minimum norm W hat of W hat. Or we're basically minimizing the norm over all of our W hats, and that's the one that we're calling our best. Now, this strategy is actually applicable when we don't necessarily have an operator, but we have a map, meaning when U and V are not the same. And when our, well, let me just write these down. Same thing happens if M is less than N. And let's go back and remind ourselves what capital M and N are. M is how many measurements we've taken, and N is the unknown vector. So now we've taken fewer measurements than we have components in our unknown vector W. So if capital M is less than N, this situation is also many to one. We have a non-trivial null space and non-invertible. Or this you might hear referred to as your system of equations is underdetermined. We may not have as many measurements as we have basically unknowns W. Yes? So yes, this one, the question was right here, I think. So now, if we have a non-full rank operator, then we do not have an inverse. So we have no inverse here. Now we're just saying, oh, we can actually address all of these next few points the same way, so let's just do it. So this led us to the case where we do not have an inverse. Now we're saying, oh, in these other cases we aren't going to have an inverse, and we're actually going to find that all of these lead to the same pseudo-inverse. Since the true inverse does not exist, here we've said, oh, we started this path when we had an operator and we didn't have full or a complete set of linearly independent rows or columns in our matrix representation of this linear operator. So we know that we didn't have an inverse there. Now we said, well, let's just go ahead and cover more bases before we talk about the pseudo-inverse, and this is the first base, or let's say the second base if the earlier one is our first base. We're going to get to second base next. But this is the underdetermined case where we have fewer measurements than unknowns. So if you wanted to think about what's the structure of the matrix representation of T, that sort of has this shape, doesn't it? It's short and wide. This is now the structure. So we have many more unknowns than we've taken measurements on. And this, it should be clear, has this non-trivial null space. But even under this condition, we still want to find the best W hat. Since we have a non-trivial null space, we have many different W hats. We want to find the one that's the smallest, or the smallest in norm. Again, we seek to find a minimum norm solution. So there's the second possibility. And again, it's saying let's seek the minimum norm solution. If we go to here was first base with the operator. Then we went to second base when M was less than N. We can actually look at the case where it's overdetermined, where we have more measurements than we have unknowns. If capital M is greater than N, then this system or the measurement system is overdetermined. So it might be possible to find a unique solution. But again, we're dealing with a non-square matrix representation of this linear operator, capital T. It's now not square. Now we have three different cases, three different bases. That's maybe a bad term, but now we have three different situations where we have a matrix that doesn't possess an inverse, the typical inverse. Now we will give a strategy for basically addressing that. All situations can be addressed by finding a reconstruction let's say operator P that we will select to minimize the error between T applied to our estimate, W hat, so T W hat, compared to the measurement M. And the error that we will create is just the norm squared of that difference. So we're creating an error which is just the norm squared of the difference between TW hat. W hat is our best estimate, M is our measurement, and T is our linear map. And what's inside that norm is obviously a vector. We're boiling that down to a scalar. And do you remember how we maybe did minimization problems in calculus? You always were worried about the derivative and setting that equal to 0. Well, you can actually now differentiate this with respect to the estimator, or the vector that we are estimating, which is W hat. This norm squared, how would we write that? Or what's another way of writing that norm squared? As an inner product. So now we have an inner product of TW hat minus M with itself. You can distribute that all out and get these individual pieces and take the derivative of that expression with respect to this vector W hat. And what you will end up seeing is that you end up with 2 times the adjoint of T multiplied by T W hat minus M. So there's the partial derivative, or the derivative, and we want to minimize that, so that says that we want to set that equal to 0. Now let's just see what that translates into if we just use this equation or this relationship. Well, the 2 is just a constant. We can divide by 2. That's a positive number and not change that relationship. And let's now distribute that adjoint through the 2 remaining terms. So now we have T dagger T W hat minus T dagger M. Or if we put T dagger M on the right-hand side, we have T dagger T W hat is equal to T dagger M. But what do we know about T dagger T? It may be possible that that has an inverse. Let's say that T was, let's say, tall and narrow. Then T dagger will be narrow and wide. We multiply T dagger by T, and we now have this possibly square, we will have this square operator, T dagger T. So let's now assume that that inverse exists, and that now says that W hat, or the best estimate, will be T dagger T inverted times T dagger scaling the M, or operating on the measurement M. And this collection of operator, the product of that, is the Moore-Penrose pseudo-inverse. This P equaling T dagger T inverse times T dagger is the Moore-Penrose pseudo-inverse. Now, where are you wanting to cancel T dagger? Oh, here. So the question was, why can't we just cancel T dagger? It's a matrix and it doesn't have an inverse. So we can't when we cancel things in equations, what are we usually assuming? We don't even think about it, but we're assuming that they're not equal to 0, right? So we can divide them out. Well, if it's a matrix, if it has no inverse, that's like it's equal to 0. We can't divide by 0 in the matrix case. So this T dagger, we can't just divide it out. Its inverse doesn't exist. T didn't have an inverse, so its adjoint won't have an inverse either. But it's very possible that T dagger T will have an inverse. And that's what we're using to find our best estimate, W hat. And now this pseudo-inverse is a collection of 3 operators. Okay, and let's now just make some comments or write down some observations or notes relative to this pseudo-inverse. One is the one that is sort of the elephant in the room that I've been talking about. Suppose T dagger T is not invertible. Now the nice thing is it is always square. Then it can be shown that if we define the pseudo-inverse P to be the limit as epsilon gets small in the following expression, T dagger T plus epsilon I, that does have an inverse for a small positive epsilon times T adjoint. This P always exists and minimizes the error. So if it turns out that T dagger T doesn't have an inverse, then what you do is you find the size of T dagger T. What are its dimensions? It's now an operator. That's now giving you the size of that identity matrix. You scale that identity matrix by a small epsilon, and that will actually now allow you to invert that parenthetical expression. And that then gets scaled by or multiplied by T adjoint. So even if if T dagger T is not invertible, you can still use this formula to obtain an answer. Here's what I like. This pseudo-inverse P can be easily obtained from the singular value decomposition. Suppose that this linear map T, and now T doesn't have to be square to possess a singular value decomposition. T can be anything. It can be short and wide. It can be tall and thin. It can be square, the matrix representation of that linear map. But the SVD says that we can now factor that into U. And what are the columns of U? What's special about the columns of U? Have you watched that material on the SVD? U has orthonormal columns, and it has as many columns as rows. It's square, and so however many rows you have in the matrix representation of T, that's how many columns you are going to have in U, and those columns will be orthonormal. So that's one piece. I haven't completed this yet. It's a product of three matrices. Sigma is a very sparse matrix. It only has diagonals in the upper left-hand corner, and those diagonal entries are the singular values of this linear map T. So let's say that we've now found the singular value decomposition of this linear map T. Then we want to find the pseudo-inverse P. P is now V, where V is just the transpose of V transpose. So the vector V, the matrix V is also made up of orthonormal columns. And U and V, those columns can be partitioned to find the four fundamental subspaces of a matrix. A very beautiful concept with the SVD. But now we are basically reordering the product of U sigma V transpose, except we are now inverting the non-zero terms in sigma. So I'm going to represent that by this matrix that I will call S tilde times U transpose. Oh, sorry, may I change my notation? Instead of the Greek symbol sigma, let me just call that S. So this is now US V transpose. Usually the singular value decomposition is U sigma V transpose, but to be consistent with what I'm going to say now, let me call that S. It's still this it's a matrix that in the upper left-hand corner is diagonal with non-zero singular values in that diagonal location. So S is now diagonal, where those are the singular values, the non-zero singular values, and if there are zero singular values, those will be zero. Then we're defining S tilde to also be a diagonal entry, but we're only dividing by the non-zero S sub I. So that now we have 1 over S sub I for S sub I not equal to 0, and 0 for the 0 entries in that matrix capital S. And if the singular values are tiny, you could just say, let's just assume those are 0 and not worry about inverting them, and just set those to a hard 0 also. Meaning, if you want the pseudo-inverse, you can find it from the singular value decomposition, where you simply take the U and the V matrix, these are orthonormal matrices, and their inverse is just their transpose. And all the fancy stuff that you have to do then is look at the singular values in S, invert the non-zero ones, and place those into this new matrix S tilde. And then the pseudo-inverse is V S tilde U transpose. That's the second note, that we can find this pseudo-inverse or build it or construct it from the singular value decomposition. The third note or comment is if T let's say if T is invertible, then what happens? Well, if we look at P, that was T dagger T inverse times T dagger. If, in fact, T is invertible, what do we know about this product of T dagger T? Well, then T dagger will also be invertible, and if we have a product inverted, how do we write that, or its inverse? How do we write the inverse of a product of operators? We just reverse their order and invert those matrices or operators. So in this case, we would have T inverse times T dagger inverse times T dagger. And now this, on the right-hand side, that matrix product, we have T dagger times its inverse, that's the identity, so that we now can write T inverse times the identity, or this pseudo-inverse collapses to just the inverse of T. Or another way of saying that is, if you don't know what you're dealing with, you can compute the pseudo-inverse, and if in fact T was invertible, it's going to fall out as from the definition of this pseudo-inverse. So it works in all cases, that pseudo-inverse. That's chapter 10. Or what I wanted to cover in chapter 10. What I have are there questions? Let's now just sort of set up what we'll talk about let's say I'll provide a different lecture to this, a little, let's say 30-minute video from before. But let me just see if I can set up this PCA, or principal component analysis, problem in the time that's remaining. Question. Suppose we are given a set of vectors. Maybe we call those S, so don't get these confused with the previous S that I was using to be this diagonal matrix. This is now just a set of vectors X, S, in a finite dimensional vector space, which we'll call capital V, with the dimension of that vector space being n. So in this particular analysis, we're basically saying somebody's giving you this carton full or this box full or a treasure chest full of vectors. And you're trying to maybe reduce the amount of information or get the most important pieces of the information out of that collection of vectors. So given a set of vectors S in a finite dimensional vector space V, where the dimension of that vector space is capital N, what is the shortest list that can represent a vector, let's say X, in S? So that's question one. And probably most questions that are asked, you could always answer it with the following: it depends. So the answer that we are giving is really that it depends on what we are given with this set of vectors S. So our answer says it depends on S. Let's look at some examples of this. Suppose that somebody starts with the underlying vector space being R2, and this we can sketch. And maybe they give you a collection of vectors that are in R2. Meaning, if we now have two coordinates, let's say x1 and x2, we're living in R2, and somebody says, oh, what's the list that you need if somebody wants to parameterize an arbitrary vector x? An arbitrary vector in R2. How big of a list of vectors would you need to specify any given point x in R2? If you don't know where it is in the space, you don't know its angle, somebody says, I want you to represent an arbitrary vector in R2, then to fully represent that, you're going to need two vectors, aren't you? You're going to have to find a basis, which needs to span R2 and be linearly independent. So for this, you would actually need a list of dimension capital V equal to 2. Contrast that, let's say, with the following. Suppose that somebody said, well, here's some data. And those data points, I'm not wanting to shade those too much because sometimes my machine will assume that I'm erasing that, which almost happened. But now you have this collection of points, and somebody says, can you reduce that down? And now, if you could maybe just identify that line, now you could represent, in a sense, this general scatter of data points by one vector. That's sort of the principal component of that collection of data. And now you can see how this generalizes to a higher order collection of data points. Maybe you have a collection of data that may be 100 in dimension, it may be 100 dimensions. But now you can maybe identify, one or two or three major directions that those data points live in this 100-dimensional space. And that's the idea behind this principal component analysis. And I'll try to post a shorter little collection video that helps talk about that beyond this point.